All right, so up now, Cluster Inspector by Galaxy Next Door.
Hi everyone. So please lower your eye level to this level. I don't know how come they schedule me my talk right after the totally sky. Okay, I'm gonna talk about cluster. So when you hear about the cluster, the term cluster, what does come up in your mind first? What do you think? What I'm gonna talk about? You already know, but yeah. So what's your favorite cluster? If you think about, if you think about the computer cluster first, that's I think that's one of the beautiful picture. You see all those multiple computers processing all those different data at the same time. Can you imagine how fast it would be? And yeah, I think it's awesome. And that computer cluster is actually particularly called ALMA correlator. ALMA is an array of radio telescope in Atacama Desert in Chile. And those array telescopes collect all those data, and the ALMA correlator compute as make those data set as data from the one single telescope. So that's one of my favorite cluster also. What's next? As you know, I'm a pet, husky puppy cluster. That picture, I actually took it by myself at the Denali National Park. So they rarely get those puppies. But these are how many puppies? Can you count? They're all clustered together. So there are 8 puppies, husky puppies, from the same mother. So remember, they are from same mother, so they share the same DNA or the same gene. They tend to always sleep together, play together, stay close together. That means they're at the same distance from us, right? They're always like that. And also, they are also born at the same time, so their ages are same. But you can see a little bit of differences between each puppies. What do you see? Their colors are slightly different, and they might be growing in a different size. Yeah, you can see the different combination of different colors. So keep that in mind. Those information will be important to understand the clusters I'm going to talk about next. So cluster I'm going to talk about is star cluster. So term cluster we use to describe a group of similar things or peoples. And as you saw, I talk about the computer cluster, similar CPUs or processors and similar puppies. And those star clusters are made of similar stars. And they're also born at this, go to the next one. So those stars in clusters, they're born at the same time, meaning they have the same age or similar age. They are born from the same molecular cloud, mother cloud. So they share the same chemical composition. We call it metallicity. And they are gravitationally bound. So they stay together, similar distance. So it's easy. When we measure the distance of one star, we can assume all those stars in the clusters are at the same distance. But they all have different mass. And the mass distribution follows the function called initial mass function, IMF. So those are the properties we use to understand the star clusters. And those star clusters are also important to understand the galaxy, because galaxies are made of stars and star clusters. So we call those star and star clusters are building blocks of the galaxy. So let me go back to one slide back, and let's see how the star clusters are formed. I don't know. So this simulation shows how those star clusters form from the molecular cloud. And the mass of the molecular cloud is a 500 solar mass, meaning 500 sun-like stars. So it's a low end of star cluster mass. And you can see the dense part of the cluster start to see forming stars. Do you see all those little dots? Those are stars. And the dense part, so when they reach to the certain density, they start to form stars. Not everywhere in the molecular cloud. So there's a mechanism called turbulence. So turbulence work in those smooth distribution of a molecular cloud. And you see some of the stars are kicked out. And one of our colleagues studied all those low mass stars kicked out from the star clusters. But still, vast majority of stars stay together, still gravitationally bound, and they born at the same time, so same age as I mentioned. So those are the how the star clusters are formed. And this is the size of the simulation is like 3 light years across. So it's a very small portion of the actual star cluster. And those are star clusters I study. And there are 2 different types of star clusters. Globular clusters versus open clusters. What differences do you see from this image? You can learn a lot from the image without doing any types of serious analysis. What do you see from this image? Can you, sorry? Yeah. And the major difference is actually really easy to see. Colors, right? So blue stars are in the open clusters, and in globular clusters, what kind of color do you see? Like red, orangish, and also number of stars are different. That means the size of clusters are slightly different, and also the shapes are different. So globular clusters, as the name says, has a highly symmetrical distribution. So you can see the smooth distribution of stars. And all those red stars are bright red giants. So they tend to have older stars. And red color, like astronomers like to flip all those common sense. So red stars are actually older and a little bit cooler than blue stars. And those blue stars are hot, young, massive stars. And particularly the open cluster on the right side is called Pleiades. And that's one of the famous open clusters. You can see it with naked eye, like without any binocular or telescopes. You can go outside now and just stay outside for a little bit longer for your eyes to get dark adapted, and you can count those individual stars. And do you know one of the motor company named after the star cluster? Do you know? Yeah. Have you paid attention to the logo of their company? Have you ever counted how many stars in that logo? A little bit more than 4. It's I think they have a 5 or 5 small stars and 1 big cross, so 6. But the nickname of that open cluster is actually 7 sisters. You can see 7 bright stars. If you go to a darker place, you can count more than 7. So also another main difference is you see a little bit fuzzy clouds around those massive stars. So open clusters tend to still have some of the molecular cloud or gas around because they are young massive stars and they are also heat up the gas around. But globular clusters lack of any leftover gas. And in our Milky Way, they don't form globular cluster any longer. Those are all formed in the earlier universe. But we're still forming the open clusters. So open clusters are younger, globular clusters are older. And globular clusters have the stars around 1 billion years old, and open clusters tend to be million years or slightly older than that, but still way younger than the globular clusters. And I don't know how, if you can count how many stars in the globular clusters here. A lot, 100,000 of stars. But open clusters have thousands or 10,000, so different system. So these 2 examples are very clear. It shows a very clear distinction between the globular clusters and the open clusters. Let's look at this. Can you see? The first top left one, it's easy. Okay, that's globular clusters. But that one is very tricky globular cluster. It's called omega sen. So as I mentioned earlier, we think all those clusters are born at the same time. So it's easy to think all those stars have the same age. But the omega sen is very tricky because they have 3 different stellar populations, at least 3. So their ages are different, their metalysis are different. So it's a complicated business to understand those globular clusters. And what about open clusters? Do you think they look like clusters? This is just a sprinkle of stars. It's hard to tell if they are member of cluster or just stars wandering around. So it gets more difficult. And these clusters are all in the Milky Way, our own galaxy, or neighboring galaxies like Magellanic Clouds. But if we go to the external galaxies, a little bit more distant galaxies, it's really difficult to identify which are the clusters, which are the stars, because they all look the same. Let's look close. Okay, let me explain what this one is. This is a barred spiral galaxy called M83. M stands for Messier, the person who identified a lot of fuzzy objects in the sky. This is the galaxy I spent a lot of time in graduate school. It's a beautiful galaxy, and you see all those magenta color bubbles. That's where all those new stars are formed. As I mentioned, all those massive young stars are very hot. They heat up the gas around, and that generates those pretty bubble. I mean, the color is a false color, but still, it's pretty. And you can see those star-forming regions along the mainly spiral arms. But if you look really closely, I don't know if I can use the pointer here. Yeah, can you see my pointer? Yeah, there are star-forming regions here, and also very tiny star-forming region here and here. It's everywhere. This galaxy is forming stars everywhere, especially at the center. We call this galaxy as a spiral galaxy with a star-bursting core. There is all sorts of crazy activities at the center. I don't know if you've heard about Hwihyun stars. That's predecessor of some of the supernova explosion. And so there are at least 15 Hwihyun stars known in this central region of the galaxy. So that's M83. Let's look closely, only for the top part. Let's zoom in a little bit. How many clusters can you count? It's really hard to count. So let me point out one. This is one of the clusters. So in the extra galaxies, it's hard to tell if they are open clusters or if they are globular clusters, because all those stars are on top of each other, and it's more distant. So this galaxy is actually at the distance of 15 million light years. It's really close. It just takes 50 million years to get there if you travel at the speed of light. It's way closer than the galaxy Rachel studies. So yeah, it's still neighborhood. Galaxy next door, right? That's my name. Yeah, so let's look at this cluster and this cluster. Can you remember this one and the one at the bottom? Can you tell the difference? Looks very similar to each other, but there's a slight difference in color. So the top one is bluer, and the bottom one is orangish or reddish. And if you look closely, wear your glasses, and this one has more red stars on top of it. The distribution is not as smooth as the bottom one. So we think the top one is younger than this one, the bottom one. And also there's a nasty business called dust extinction, but we're ignoring that now for this purpose. So let's compare that cluster to clusters here. Do you remember all those magenta bubbles are the signature of newly formed stars? So there are clusters inside of that bubble. They are younger than the cluster without those bubbles. So that's how we distinguish the ages of different clusters. This cluster, I call it croissant because it's arc shape. Everything is about food. and this cluster is multiple star forming activities, and it's blowing off that magenta bubbles. So it's slightly older than the clusters still embedded in that hydrogen gas. So that's how we tell the story of star formation history of this galaxy. And if we go back to the entire galaxy, there are multiple different regions like that. So we use star clusters to understand the evolution history of the entire galaxy. And there are tons of these types of galaxy. So my colleague and I started a survey called LEGAS. So when we discussed the name of the survey, there were like many different candidates, and we picked Legos because it sounds like Lego block. Because star and star clusters are building blocks of the galaxy, and we study galaxies to understand the universe because galaxies are building blocks of the universe. And the LEGAS stands for the Legacy Extragalactic UV Survey. UV is ultraviolet light, and that's the unique about our survey. So we use ultraviolet image to understand the hot young stars. So if you are the frequent, customer to Astronomy on Tap, you know the electromagnetic spectrum from the X-ray, gamma ray, X-ray, UV, visual, infrared, right? And you mentioned the 660 nanometer, that's great. That's the visible light, our eyes are sensitive. UV light, we can't really see. We need to go to space. So all those survey data is from the Hubble Space Telescope. And like the Mike Maximino, thanks to the taxpayers, so we had this last service mission in 2009, so they installed a new camera. And that new camera had very high sensitive UV camera called wide field camera 3. So third generation of wide field camera. And also they have IR camera, infrared camera too. So UV light, all those hot, massive young stars are bright in UV, and cool stars are bright in infrared. So just keep that in mind. So let's see what we learned from the UV light. That's the optical image of one of the galaxies in our sample, NGC 6503. It's also close, 70 million light years away, in the Draco constellation. It's near the Big Dipper. I don't know if you can see all those bubbles. I don't think you can see that, but there are like star-forming regions along the spiral arms. This is a dwarf spiral galaxies. Spiral galaxies, but it's a smaller spiral galaxy. You can see the nucleus is also small. So that's optical image, like you can see with your eyes. And let's look at the UV. So UV images reveals more massive, hot blue, massive stars. Let's go back. So all those UV lights are hidden. So yeah, that's the difference. So we can learn more about those massive stars are very bright in UV, shorter wavelengths. So we are using those UV images to understand the recent star formation, because all those hot young stars are very bright in ultraviolet light. If you don't observe that portion of the electromagnetic spectrum, you're missing a lot of information about those massive stars. So these are examples of 8 galaxies. We have 50 galaxies in total in our sample, and those boxes are just the position of points, because Hubble telescope is big, so and these galaxies are nearby, so we can really see the whole region at once. So we need to point the telescope to the different positions. So our sample covers different size, the galaxies in different sizes and with a different star formation history. So what we do is we first make the star cluster candidate using the tool called source extractor. So we extract all those star cluster candidates, because where they are is also important information to understand the galaxies. Then what we do is clean up that cluster list. So this video is actually recorded on my desktop. I tried multiple times not to mistype anything, so that's what I do. So you type the galaxy, and we use the color information and also image of the image from the Hubble Space Telescope. And you can see I changed the contrast to see the distribution of light, and I also changed the color image just to see how different those distribution in each different colors. And we check the radial profile of that cluster candidate, and it goes fast. Ellipse fitting, and that's the surface fit. So those information I collect and determine the class, what type of cluster it is. And that's one of our galaxy called M51, Whirlpool Galaxy. That's another example. It took a minute and a half to classify 2 clusters, but actually it takes longer than a minute and a half, because this I took 3 times to not to make any mistake. So again, how can I go to next one? Yeah, so we use color information because color gives us a lot of multiple different information in the image, and use the radial profile and surface field and list fitting to see how the lights distributed in different filters. So we came up with 4 different classes. So first class is a very symmetric and compact and very nice clean cluster. We call it, oh, that's a definitely cluster. And class 2 has elongated distribution, and class 3 has multiple peaks. So it's more like open clusters, but we don't call them open clusters. It's just, we call them association. And class 4, we just ignore them because they are miscatalogued by that tool called the source extractor, because the example I'm showing it there is the stars are between 2 other stars. So the software we trust with our life, they think that is cluster, but actually not. So without checking individual cluster candidate, you will classify that as a cluster if you don't check every possible cluster candidate. So that's what we do. And of course, I cannot do everything by myself. I have 14 people helping me. And we also hired the undergrad students because we believe undergrad students have a lot of time to do these things, click, click, click. And some of the undergrad students started dreaming about the star cluster and blaming on me, so we're so sorry. Yeah, so the reason we are doing this individual checking is, I don't know if you can see all those black dots. So if we don't do those visual inspection, all those, that's bummer. Well, these are the, each points are the cluster, and the black dots are the cluster candidate from that automatic software, and the blue lines are the model. So we use the blue line to determine the age and other properties of the mass, age, metallicity, everything. So these 2 plots are, it's a color versus color plot, different colors. And if it's a negative value, it's blue. So if those clusters are blue-blue, that means they are very young. And if they are red-red, they are old. So you can see the age marker here, 1 million years, 1 billion years. So after the cleaning up the catalog, those points are on top of the models. That's what we want. And as I mentioned, we cannot really do everything by ourselves, because particular case showing here, M51, they have we came up with 10,000 clusters candidates. So a minute itself, still 10,000 minutes, it's too much. And we have 50 different galaxies, and of course, some of the galaxies have just 20 cluster candidates because dwarf galaxies have less number of clusters, but still. So one of the graduate students at University of Massachusetts, she came up with this idea, cluster zoo project. It's a part of the universe, and we haven't launched yet, so there are a lot of things we need to clean up before we launch that website. So I think they are doing the testing. So stay tuned, and please help us to identify all those birthplaces of the stars. And that's all I have. I don't know how to go back, but yeah. So thank you for listening. So yeah, we need Penny and Brain, like the Inspector Gadget.
I always wanted to be Penny when I was a kid.
Yeah. Oh, I wanted
so I'm going to start off the Q&A. I think I heard you throwing shade at my blobs. It's all very well looking at galaxies right next door. Sure, they're shiny.
Okay. Redshift people always use our galaxy range.
That's true, actually. Yeah, we do. No one wants to look at our pictures. Okay, so any questions for Dr. Kim? Down here.
Yeah, go ahead.
Okay, so the sun, odds were, was born in a cluster as well, right?
Yeah.
And any chance of finding any husky puppies that were born with the sun?
Can you repeat the question?
So you were asking, is there any chance I can find the husky puppy clusters in other like sun-like stars, or like the husky puppy? I stopped. Like my brain stopped.
Other stars that were born in the same molecular cloud as the sun.
Oh yeah, there are like the nearest star from our sun is actually 4 light years away. But sun is a kind of unique star because most of stars born in a like multiple star system, binary system or triple star system. So we are part of the star cluster, but still like the nearest star is 4 light years away. So
It was born in the same molecular cloud as the sun.
yeah. Yeah, molecular clouds, size of molecular cloud is bigger than just 3 light years away. So the giant molecular cloud, we call it giant molecular cloud, the size distribution varies from the 3 light years across up to 30 or 300. So it depends on the environment. So if the galaxy is, well, full of gas, if they are formed from the rich environment, they tend to make the bigger molecular cloud, but there's also physics limiting the largest molecular cloud. Of course, they cannot really have galaxy-sized molecular clouds, so there's a limit, but still, yeah. 3 light years is a very tiny molecular cloud, so we don't call it like giant molecular cloud, but yeah.
Okay, we've just got time for one more question. I think I see one straight up ahead up there.
Spiral galaxies are centered by a massive black hole.
So the question is, how many spiral galaxies are centered by the black hole? So we believe all those galaxies have like black holes at the center. Some of the galaxies believed to have a multiple black hole, but that makes all those star forming activities crazy. And I think M31s are believed to have one, but has 2 cores. So I'm not the expert about the black hole, but most of galaxy, we think there's a black hole. But someone can maybe give the better answer, but yeah.
Yeah, that's a good answer.
Yeah.
All right, let's say thank you very much to Galaxy Next Door again.
Thank you.